a part 2 of the presentation, and by the end of this presentation, we're going to understand the difference between a static field and a pulsating electromagnetic field. We're also going to discuss the many devices on the market that people are asking about to reduce EMF radiation in the house and around them. So we'll go over each one and how they're supposed to work and how they may not work as well as we think. So let's start with some basics here. And I've been getting several questions offline about the difference between a field that is a constant field, like direct current, which you would get from a battery, versus an alternating current, which we showed in the video. This short segment will never give you enough information to learn enough about what's happening, but I'm going to try my best to describe what's going on. So with a basic circuit, you may have done this in high school or even grade school, where you take a battery, connect a wire to a lamp, the lamp turns on. Electrons are flowing out of the battery, through the wire, of course, into the light bulb. There's a little bit of resistance here in this filament, which is required in order to get your light to turn on. And then the electrons return back to the battery. And you notice I'm using non-conventional flow. Electrons actually move in not positive. I know people are used to seeing that way, but anyway, let's not get into that. Let's just pretend current is flowing this way. When the light is turned on and there's current flowing through the wire, there is a magnetic field that builds around the wire and it stays constant. Constant in the respect that this battery would always have unlimited energy, and we know that's not the case, but the field is going to stay constant. It's not going to pulsate, it's not going to change polarity, so to speak. It's going to stay relatively consistent. The variables that determine the size of that field are the amount of volts that come out of this battery, the amount of energy coming out of the battery. This could be a 5 volt, a 1.5, it could be, let's say, 100 volts. And the second variable is the resistance of this bulb. So the brighter the bulb and the more voltage, the bigger this field will be around the wire. Okay? And the closer you are to that field, the more energy you're going to absorb. However, a constant static field is not as dangerous as an alternating one with high frequency. So when you're next to a DC source, you don't have to be too concerned. It's just like building up a static charge from rubbing your feet on the carpet, and then you touch a door handle, let's say, and you ground yourself and you feel that zap. Well, your body had a potential charge on it, a voltage, but you don't really feel it because your entire body is feeling that same energy. There's no distinguishable difference until you touch ground, and then you give yourself a path to discharge all that energy. So that's essentially what a static field looks like. Okay, here we go. We have a magnet, north and south pole, and you take that magnet, we'll choose one pole. I should have drawn a bar magnet, I'm sorry. Let's try like this. We're going to take this end of the magnet and move it toward the wire. As you move the magnet toward the wire, the magnetic field of the magnet is going to induce the field into the wire. And we have little electrons in here that are standing still right now. But as soon as I move this field closer to the wire, right, we get, if this is the starting point, I'll make a little graph. You're going to see how this happens. This is positive energy, and this is negative energy, for sake of argument. This is the magnet starting in this position, and this dot will represent the field in the wire. So as I move closer to the wire, the field gets stronger. When the magnet is here, that would be the peak. As we keep moving across, the field is going to get weakened because we're moving away from the wire now, so it's coming down. Okay? And then if you can imagine the south end of the magnet, as we move it over, it's got an opposite charge. So when the north side of the magnet goes closer, these electrons move, let's say, this way. So we come closer, electrons move, let's say, up the wire. Okay? And then the magnet is here, that's the peak. And then as we move away, we're here, and current flow stops. Now let's pretend the magnet is on this side of the wire, north and south is now here. This is the end of the magnet, and we're moving this pole closer to the wire. Well, now, because it's an opposite charge, you know that it's going to start to move the electrons in the wire this way, this way. So now they're going to start coming back down this way, and you're going to get this until the south pole of the magnet is at the very center of this wire, and then it's going to come back up after we fully move the magnet across. Okay, so that's how we get our 1 cycle per second. In order to do that and create a usable amount of energy, we would have to move that magnet very quickly, and we would have to move it across, bring it back 60 times per second, and that would be quite a task for a human to do. So what happens in our hydro stations is we use water, and that water turns a turbine, and that turbine inside has a magnet and a coil of wires. So we're using the water as the force to turn the turbine to create this energy waves 60 times per second. That's how we get alternating current. Now, remember when I said I would have to move the magnet across the wire very forcefully, very quickly, several times per second, in order to get a usable amount of voltage or current, however you want to discuss this topic. What I've done is I set up a little circuit here. I've got an oscilloscope, and I'm measuring the magnetic field. I have a magnet here, a very strong one. And I'm going to show you on the screen. All I'm going to do is this. I'm going to show you what I'm doing, and then on the screen you might see, I can see the reflection. Let's see if we can focus in on that a little more. It's very difficult to see, but you can see it moving very slightly. That's not enough energy. Here, you can see it now. Not enough energy to be of any use. Couldn't do much with that. That's a very, very small peak of voltage. So you can imagine the amount of energy required to produce the electricity that we use in everyday life. Yeah, the first device we were asked about was, I'm not actually going to say the name of the product, but I'm going to give it a decent review because it does what it says, although it's very expensive for what it is. We have to understand that the energy on our hydro lines produces an electromagnetic field just like anything else, because it has a frequency, it has a current, it has energy. So the closer you are to the incoming power line in your house, where the meter is, that's going to be the biggest source of AC 60 hertz in your home. So if you have your bed next to that meter, I'm not talking about smart meter, I'm talking about the power meter, the one that is used to measure the amount of energy used every month. If your bed is next to that big thick wire carrying all that current into your home, you may want to move it around, because that's a big energy field to be sleeping in, and it's not good for you. So this box claims to reduce electromagnetic fields in your home based on the energy in your outlets, not in your atmosphere, so to speak, not the cellular signals coming into the house or the Wi-Fi box. This is specifically referring to the fields that are occurring around the electrical box, the electrical panel, your outlets, and that sort of thing. And he talks about dirty electricity. And for me to, I guess, describe what that means, I'm going to have to give you a little quick lesson on how the AC is filtered in your house. So let me see if I can draw it for you and make some sense out of it. Better yet, instead of draw it, I can simulate it with my little toy here. It's called the oscilloscope. If you didn't pick up on that earlier, the energy coming into your house may not always be clean. What I mean by clean is something like this. Nice and stable, perfect, 100% fantasy land. Well, that doesn't always happen, because there are surges and interference on the line coming off the hydro poles. Other atmospheric interferences like thunderstorms and energy of that type. And it tends to make the electricity coming into your house look something like this. It's just not as pretty. It's got little spikes on. Here we go. Little spikes on it. It's still usable, but it's kind of dirty, as he says. So his box is attempting to make your signal nice and clean, get rid of the spikes, absorb the surges, which you would get, like I say, from, well, you plug in another device like a vacuum cleaner, and sometimes you see your lights dim momentarily. That's due to the drain on your electrical system. But that sort of thing is happening constantly. You may also have surge protectors on your power bars, and it would do the same thing, but not to the extent of this power box, from what I understand. So that's what this product is attempting to do. I'm not sure how it would reduce the electromagnetic field, however, because we're not really changing the amount of power coming in. We're just cleaning it up. So that's the only thing I'm a little uncertain about, because whether or not you clean it up to this, you still have quite a bit of energy there. So the claims of reducing the field, I don't know. I still, without a meter, wouldn't be able to verify it. If someone has this installed in their home and can get a field meter and measure the difference with it plugged in and unplugged, I would love to know. But theoretically, if there's a little bit of a difference, I could see that, but it's not life-changing, so to speak. It's not going to get rid of the field entirely, because you still have energy going through wire. Next product we're going to talk about is this USB device that claims to reduce EMF in the house, and this is the EMF coming in from TVs, cell phones, Wi-Fi routers, cell towers. Okay, so let's discuss what's happening in the house and around us outside and everywhere we go, and then we're going to discuss what this thing needs to do in order to reverse that field, and you can make a decision on whether or not it's the right product for you. So let me pause, and we're going to look at, we're looking at this ripple in the water, and this is more or less what the antenna would be emitting, and this is, you know, similar to what we'd have in the atmosphere around us in the house or as we're walking outside. There's energy emanating from a source, and it's spiraling out or banding out in circles, and the energy gets less and less as it gets away from, in this case, where the rock is thrown, but it dissipates as it gets further away from the source. So we have to, in order to reverse this wave, we would need an opposite energy. So instead of the peak of the wave happening at this point, we would have to have a trough or a negative wave going into the water, not out, to cancel this wave. So I'm going to show you what that looks like on paper. We'd also have to be in time or phase with all of these ripples. So we cannot have the wave happening at this point in time. It would have to happen at this point in time. It would have to move at the same speed or frequency, and it would have to be the same amplitude in order to cancel it out completely. So let me draw that on paper for a second.